Welcome back to our class on algorithms and data structure. We're continuing to make some good progress as we go through these different data structure types. We've talked about bags, we've talked about stacks, we've talked about queues, and now we're completing the discussion on lists. And so this lecture, what we'll focus on is a list implementation that links data. So to that end, let's get into the material here. And so here is the material that's in the textbook. So you can look over that at your leisure, and we'll be covering this information. So the chapter describes a linked implementation of the list. Like our previous linked implementations, this one uses memory only as needed for a new entry and returns and any unneeded memory to the system after an entry is removed. Moreover, it avoids moving data when adding or removing list entries. These features make this way of implementing a list an important alternative to array-based approaches. So what are the advantages of linked implementations? It uses memory as needed. When entry is removed, unneeded memory is returned, and avoids moving data when adding or removing entries. So using an array to implement the ADT has both advantages and disadvantages, as we saw before. An array can either have a fixed size or be moved to a larger array when it becomes full. Since a fixed size array can lead to a full list, our class A list uses a resizable list array to provide as much space as the list needs. The strategy, however, requires data to move each time that the array expands. In addition, any array requires you to move data either to make room for a new entry or to close up a gap after a deletion. So in terms of adding a node at various positions, there's several possible cases that we have listed here. So let's talk about the operation on a chain of linked nodes. We used a chain of linked nodes in chapter 3 to implement the ADT bag, and in chapter 6 to implement the ADT stack. In both those cases, we added a node to and removed a node from the beginning of the chain. We added a node to the end of the chain in chapter 8 for one implementation of the ADT queue. While those operations are still needed for a list, we also must be able to add a node between existing nodes and to remove a node from positions other than the beginning or end. So we'll talk about these operations here as we get into this chapter. What about adding a node at various positions? To add a node to a chain at a specific position, we must consider the following cases. One, the chain is empty. Case number 2, adding a node at the beginning of the chain. Case number 3, adding a node at between adjacent nodes. And 4, adding a node at the chain's end. So let's look at those first for case 1, adding a node at an empty chain. Although we have added nodes to an empty chain before, let's recall the necessary steps. First node is the head of the reference to a chain. It will contain null when the chain is empty. Figure 12.1a illustrates this state. Along with the node that we want to add to the chain. The following, you can consider pseudocode that places the new entry reference into a new node and then inserts the node into the empty chain. So what that would be is, as we show in the slide, new node references a new instance of node, place the new entry in a new node, first node equals address of the new node. Figure 11.1b shows the results of this operation. In Java, these steps appear. We can come up with an equivalent way of doing that, where new node equals new node equals new node, new entry. And first node equals new node. Notice that in figure 12.1b, first node and new node reference the same node. After the insertion of the new node is complete, only first node should reference it. We could set new node to null, but as you will see, new node will be a local variable of the method add. As such, new node will not exist after add ends its execution. Let's look at case number 2, adding a node to the beginning of a chain. This case should be familiar to you from the material we've covered already. The following pseudocode describes the steps needed to add a node to the beginning of a chain. New node, reference a new instance of node, place new node at new node, set new nodes link to first node, and set first node to new node. So the new node is now the first node. In figure 12.12 illustrates these steps and follows with the following Java implementation. So let's look at case 3, adding a node between adjacent nodes of a chain. Because the ADT list allows additions between 2 existing entries, we must be able to add a node to a chain between 2 existing consecutive nodes. The necessary steps for this task are described first here, listing with pseudocode. So new node references the new node, place new entry in new node, let node before reference the node that will be before the new node, set node after to node before link, set new nodes link to node after, set node before is linked to new node. To indicate where in the chain the new node should be inserted, let's number the nodes beginning with 1. We need to locate the node at the given position within the chain and get a reference to it. Suppose that the method getNodeAt performs this task for us. Since the method returns a reference to a node, and the class node will be an inner class of a class of list, getNodeAt is an implementation detail that we would not want a client to use. Thus, getNodeAt should be a private method. And so we can figure that out, and we can define that method later. In the meantime, knowing only what getNodeAt does and not how it does it, we can use it in the implementation of the previous pseudocode. If new node position provides a number of the new node after its insertion, we could come up with some Java statements to add the new node to the chain. That would be like new node equals new node, new entry. Well, I'm not going to read all these. These are things that are in the textbook, and so that's some available. In terms of this figure, figure 12.3a shows the chain after the first 3 statements execute, and figure 12.3b shows it after the node has been added. In this figure, node position is 3. For case 4, adding a node to the end of a chain. To add a node at the end of the existing chain, we can take the following steps. New node references a new instance of node, place new entry in new node, locate the last node in the chain, place the address of the new node in this last node. So that is, we make the last node in the chain reference the new node using the method getNodeAt that the previous segment describes. We can implement these steps in Java. Note that the number of nodes is the current number of nodes, and the current number of entries is in the chain. Figure 12.4 illustrates this addition to the end of a chain of nodes. So what about removing a node from various positions? To remove a node at the specified position within a non-empty chain, we must consider 2 cases. Case 1 is removing the first node, and case number 2, removing a node other than the first one. For the first case, removing the first node, this case should be familiar as we remove the first node in the linked implementation of the ADT bag, stack, queue, deck, and priority queues. And the steps are first, set first node to the link to the first node. First node now either refers to the second node or is null if the chain has only 1 node. Since all references to the first node no longer exist, the system automatically recycles the first node memory. Figure 12.5 illustrates these steps, and so we can see how that would look pictorially. Case 2 is removing a node other than the first one. In the second case, we remove a node at a position other than the beginning of a chain, and we take the following steps that are listed here. So Since all references to the disconnected node no longer exist, the system automatically recycles the node's memory. And we could also come up with Java statements that would do this, and assumes the node to remove is at position given position. Figure 12a illustrates the chain after the first three statements execute, and figure 12.6b shows it after the node is removed. So here is the code for private method get node at. The previous operation on a chain depends on the method get node at, which returns a reference to the node at a given position within the chain. And so recall that the specification for this method, we've already talked about that. To locate a particular node within a chain, we begin at the chain's first node and traverse the chain from one node to another. We know that the first node contains a reference to the first node in the chain. That first node contains a reference to the second node in the chain. The second node contains a reference to the third, and so on. We can use a temporary variable current node to reference the nodes one at a time as we traverse the chain from the first node to the desired node. Initially, we set current node to first node so that it references the first node in the chain. If we are seeking the first node, we are done. Otherwise, we move to the next node by executing current node equals current node dot get next node. If we are seeking the second node, we are done. Otherwise, we move to the next node by executing current node equals current node dot get next node. Once again, we continue in this manner until we locate the node at the desired location within the list. Within the for loop, current node should never become null if the method's precondition is met. As a private method, get node at can trust that its preconditions will be honored. Thus, current node dot get next node never executes if current node is null. You can enable the assert statement during the testing of get node at to verify these claims. So let's talk about the implementation. This is getting into tail reference. So imagine that we have a collection of data from which we will create a list. That is, our data will be the list entries. If the data is in the order in which the entries will appear in the list, we create this list by repeatedly adding the next entry to the end of the list. We could do this by using the list first add method. However, if we add contains to the statements in segment 12.4 that add an entry to the end of the list, the method get node at will be invoked to locate the next node in the chain. To accomplish this task, get node at must begin at the first node and traverse the chain until it locates the last node. Giving a reference to the last node, add can insert the new entry at the end of the chain. If this reference is not retained when the method completes its task, adding another entry to the end of the list forces add to invoke get node at again. The result is another traversal of the chain from its beginning. Since we plan to add entries repeatedly to the end of the list, many repetitious traversals will occur. Such cases maintain a reference to the end of the chain as well as a reference to the beginning of the chain is advantageous. Such a reference to the end of a chain is called a tail reference, and we introduced when it was introduced in chapter 8 for the linked implementation of a queue. Figure 12.7 illustrates two linked chains, one with a head reference and the other with both a head and a tail reference. So in terms of the data fields and constructors, 12.8 listing in 12.1 contains an outline of the class LList1 that implements the ADT list. Recall that chapter 10 defines the interface list interface and the classes that implement it. Define a generic type T for the objects in the list. We plan to define a chain of list nodes to contain the list entries. Thus, we need the class node, which we have used in our previous discussions, and so we define it as an inner class of LList. The generic type T that appears in LList header is the same one that we used in the class node. And we'll just continue on. This is just more of the listing, and we don't need to chat about that anymore at this moment. So let's talk about adding to the end of the list. Let's choose the method add and to array as the core methods that we will implement first. We begin with the first add method. This method adds a new entry to the end of the list, like the statements in segment 12.4. The following statements make the addition as we're showing here. Assuming that we have the private method get node at, which we defined in segment 12.7, we can complete the method and add, including get node at. This method first creates a new node for the new entry. If the list is empty, it adds a new node by placing first node reference it. If the list is not empty, however, we must locate the end of the list because we have a reference only to the first node. We must traverse the list until we locate the last node and obtain a reference to it. We call the private method get node at to accomplish this task. Since the data field number of entries contains the size of the list, and since we identify each entry by their position within the list beginning with 1, the last node is at position number of entries. We need to pass this value to get node at. Once get node at gives us a reference to the last node, we can set the last node's link to reference the new node. Thus, note that we must define is empty since add calls it, and so we add it to our core group of methods that we defined first. In terms of adding a position within the list, the second add method adds a new entry at a specified position within the list. After checking that the given position is valid, we create a new node that the new node references. We then must consider two cases: adding the new node to the beginning of the chain and adding the new node at a position other than the beginning of the chain. Segment 12.2 gives statements for adding to the beginning of the chain, and recall that these statements apply whether the chain is empty or not. Additions anywhere within are performed by the statements shown in segment 12.3, and so you can review those in the text if you'd like. So let's talk about the methods is empty and to array. The method is empty and assertions. The implementation of the method is empty could simply test that the length of the list is 0, as it did in the array-based implementation that we saw in the previous chapter. However, we have another criteria that we could use here. When a list is empty, the reference first node is null. If our implementation is correct, either criteria is fine, but what happens during development when some part of our class might contain an error in logic? We can use temporary assert statements involving the second criterion to help us catch an error, as in this version of the is empty as shown in the chart. For the method to array, by implementing the method to array, we will be able to test the previous method that we have written before we complete the rest of our list. The method must traverse the chain and copy the data in each node to an element within an array. Thus, it needs a local variable to reference each node in the chain. For example, current node could reference the node whose data we want to copy. That data is current node dot get data. Initially, we want the current node to reference the first node in the chain, so we set it to first node. To make the current node reference of the next node, we would execute the statement current node equals current node dot get next node. Thus, we can write a loop that iterates until the current node becomes null. So in terms of testing the core methods, earlier we realized that the add methods are fundamental to our class, so that they are part of the core group of methods that are implemented and tested first. The method to array lets us see whether add worked correctly, so it too is our core group. The constructor is also fundamental, and so the method initialized data fields since the constructor calls it. Similarly, since add calls is empty and get node at, there are among the core methods that we implement and test first. Although clear is not a core method, we have defined it, and so we will test it. Lastly, we define the method get length as a check that the add method correctly maintain the field number of the entries. Although it is not really an essential method right now, its definition is simple and is the same for the array-based implementation that we saw in the previous chapter. Now that we have implemented these core methods, we can test them. Since LList implements list interface, however, we first must write stubs for the remaining methods in the interface. We assume that we have completed that simple task. Let's choose the add method that adds to the end of the list for our first test. Listing 12.2, as shown in the figure, contains an example of the main method that we could use for this purpose. Notice that the descriptive output makes it easier to see whether our implementation is correct. The method display list is the same as the one that we used in the previous chapter to test the partial implementation of the class A list. You can see it in the answer to study question 4 if you'd like to see more details. Here we're just seeing the program output, and so more information to be thinking about. Okay, well, let's continue the implementation. To complete the class LList, we now define the methods remove, replace, get entry, and contain. For the method remove, to remove the first entry from the list, we execute the statement completing the class LList. Recall that the remove method returns the entry that it deletes from the list. Although the node that contains this entry is recycled, the entry itself is not, as long as the client saves a reference to it. Notice that we use the private method get node at, which we wrote originally for the add methods to locate the node before the one to be removed. This method is called only when we remove an entry other than the first one. Thus, an argument given position -1 will always be greater than 0 as a precondition requires. Also note that we do not explicitly set node to remove to null after disconnecting the node. This variable is local to the remove method and so does not exist after the method completes execution. Although we could set get node to remove to null, but doing so is not necessary. Okay, let's look at the method replace. Replacing a list entry requires us to replace the data portion of the node with other data. We can use a private method get node at to locate the node and then simply replace its data portion. Before calling get node at, we check that the list is not empty and the given position is valid. And so the implementation appears as we're shown here. For the method get entry, retrieving a list of entry is straightforward and we have it listed here. The method contains, the method contains for a list could have the same definition as the one given in segment 317 of chapter 3 for a bag. However, the interclass node now has set and get methods, so contains can appear as follows, and we have it listed. Because the ADT bag has remove method that removes a given entry, it must do the same search as contains. For that reason, we revise the definition of contains in chapter 3 so that the search is performed by a private method that both contains and remove can call. Our version of the ADT list, however, removes entries by position, not by the value of the entry. Thus, the search that contains does is performed only by contains. So let's look at a refined implementation. Refined linked implementation. Currently, the chain of linked nodes that contains a list entries has only a head reference. When we began writing the class LList, we noted that the first add method, which adds a new entry at the end of the chain, must invoke the private method get node at to locate the chain's last node. To do so, get node at must traverse the chain from its beginning. We can improve the time efficiency of this add method by maintaining a reference to the end of the chain as well as a reference to the beginning of the chain. It's pictured earlier in figure 12.7b and repeated here in figure 12.8. In this way, we avoid a traversal of the entire chain each time add is called. Adding to the end of a non-empty list is no longer required, requires a traversal to locate the last entry. The tail reference last node provides this information. After the addition has been made, the tail reference must change to refer to the new last entry. The following statements perform these steps as is shown in figure 12.9, as we're showing here. So the following version of the add method reflects the previous comments, and so we have that updated. And so adding to the list at a given position. So adding to a list by position affects the tail reference only when we are adding to an empty list or adding to the end of a non-empty list. Other cases do not affect the tail reference, so we treat them as we did in segment 12.11 when we did not have a tail reference. Thus, the implementation of the method that adds by position is listed here. So what about removing an entry from a list? Removing an entry can affect the tail reference in two cases. Case one, if the list contains one entry and we remove it, an empty list results, and we must set both the head and the tail reference to null. Case two, if the list contains several entries and we remove the last one, we must change the tail reference so that it references the new last entry. And figure 12.10 illustrates these two cases. So the following method considers the previous two cases in its implementation of the remove operation. So you can look that over in more detail as you would like. So let's talk about the efficiency of using a chain to implement the ADT list. So if we can consider the time complexity of some of the methods in our classes, LList and LList with tail, several of these methods call the private method getNodeAt as given in segment 12.7. The loop in getNodeAt cycles I-1 times in a search for the ith node in the chain. Thus, getNodeAt is big O n in general, but big O1 when the loop is skipped. We will use this observation in our analysis of the public methods. For adding to the end of the list, because the chain in the class LList does not have a tail reference, LList add method as described in segment 12.9 must traverse the entire chain of list nodes to locate the last one before it can add an entry at the end of the list. The method calls getNodeAt to locate this node. Since getNodeAt is big O n, in this case, the add method is big O n. Class LList with tail, on the other hand, does maintain a tail reference for the chain of linked nodes. Thus, its add method, as given in segment 12.22, does not call getNodeAt, and so is big O1. For adding to a list at a given position, the add method, as given in 12.11 for the class LList, can add an entry to the beginning of the list in big O one time. Adding to a list at other positions depend on the position. As the position number increases, the number needed for an addition increases. In other words, adding big O n when the addition is beyond the beginning of the list, because add calls getNodeAt in such cases, and getNodeAt is big O n. Thus, adding the add method as given in segment 12.23 for the class LList with tail can add an entry to either the beginning or the end of the list in big O one time. Note that getNodeAt is not called in these cases. For other additions, getNodeAt requires big O n time. For using big O n notation, figure 12.11 summarizes the time complexities of the operations of the list as we're showing here for the implementations that use an array in a chain of list nodes. For some operations, 2 or 3 complexities are given. The first node indicates the time required for an operation at the beginning of the list. The second is for the operation at positions within the list. And the third one is if it exists is for operations at the end of the list. Finally, the Java class library, the class linked list. Recall from chapter 10 that the Java class library contained the interface Java utility.list. This interface is like our list interface, but it declares more methods. Also, some methods have different names or specifications, and the list entries begin at position 0 instead of 1. Segment 10.14 of chapter 10 summarizes these differences. The same package Java util contains a class linked list. This class implements the interface list as well as the interface queue and deck that are described in chapter 7. Thus, a linked list defines more methods than are in the interface list. Furthermore, you can use the class linked list as an implementation of the ADT queue, deck, or list. Okay, that will end our lecture, and thank you very much.